Hey everybody, welcome to Boids and Godot using Compute shaders. For the past couple of years, I have implemented the Boids algorithm several times. It's a fun algorithm, and it's been a great way for me to learn Godot. You can see a couple examples here. One of the things that I tried to do was see how many Boids I could simulate a few years ago. I did this in a really hacky way by making three groups of Boids, and I only simulated them once every third frame. The different colors don't interact with one another. Somebody made a comment that shaders would be the way to go for this. And so compute shaders came out in Godot in 2023, and I decided to tackle this, learn how to do it. I just want to share my learnings with anyone else that's interested in this in an effort to help the community. Okay, before we get into all the coding, let's just do a quick overview here. So I'm going to provide you with a super quick explanation of what Boids is, talk through the workflow that we're going to use in Godot. Then I'll show you how to implement the particle shader for rendering the Boids. We'll do a CPU simulation first, and then we will do the GPU simulation with the compute shader. So the Boids algorithm. First step here is you find the friends, so the Boids that are within your site radius, and then within that you do a closer check to find which Boids you want to avoid. And there will be a link in the description. You can go, if you search for Boids on the internet, you'll find all sorts of information about this. So I'm not going to go into too much more detail than the high level. For the Boids algorithm, once we've found our friends, the first thing we're going to do is calculate alignment. That is basically what is the average velocity that our friends are all flying at. Then we're going to look at cohesion. So what's the midpoint of all of our friends, and create a vector that would fly us towards that. And then finally, a separation vector. That is, how do we avoid hitting the friends that are close to us? So in order to control these forces, I'm going to calculate all those vectors, but then I'm going to normalize each one of them to a unit vector, and I will supply some sort of factor, in this case the alignment vector, so I can control how strong each of those forces are. So if I want to turn down the separation, for instance, and have them all cluster much closer together, I can control that with a simple factor. So basically you'll get all of these forces, and then you will add them up to create one final velocity vector that you'll use to update each Boid. Okay, the workflow will be that we will run that Boid simulation on either the CPU or the GPU. I'm going to start on the CPU because it's much simpler if things go wrong on the CPU than the compute shaders. They're a little trickier to debug. And then we're going to collect that data. We're going to store that data in a texture map. I found that to be an efficient way to get the data from the GPU and then pass it to a particle shader. We'll be using a GPU particle 2D shader to render the Boids. And just the last piece of information I'll share before we get into this, if you need to review, because we'll use this in the particle shader, this is the transformation matrix we'll be using. We're just going to do a 2D simulation, but this is how you will basically calculate the rotation, scale, and translation in the matrix. Let's write some code. Okay, the first thing we're going to do here is create our project. I'm just going to name it Boid Tutorial. Create the folder, and then we'll bring that up. Once that comes up, we're going to create a 2D scene. I'm going to rename it to main. Then I'll go down here, I'll create a folder just to keep things organized. Call this main, that's where I want to save the main scene. Save the scene. And the next thing I'm going to do is create the main script. Okay, one thing you'll notice when you bring this project up is you get a warning about the Blender import. Since we're not using that in this project, I'm just going to go in project settings and disable that feature. I think it's important to keep the warnings clean, so if something that you do care about comes up, you'll notice it. So go and check that box, hit save and restart, that error will go away for you. First thing we're going to do here is just start simple. Going to create an array of Boids at random positions and velocities and print those numbers out to the screen to make sure we've got that working. So see here, I just create the number of Boids we're going to use, and then two arrays, one to hold position, one to hold velocity. I'm going to set maximum velocity for these Boids, and then I'm going to put in a function here that will generate random positions and random velocities. So you'll see that the first one, randef, will generate a number between 0 and 1, multiply that by the size x and the size y to give me a random xy. And then for the velocity, I'll get velocities between -1 and 1 times the max velocity. Call that function from the ready function, and then loop through the Boids and print out their positions and velocities. So let's run that and make sure that is working. And there we have our list, 0 to 99. And it looks like that's in good shape. Okay, the next thing we're going to do is set up a way to render these Boids. We're going to be using a GPU Particles 2D. I found that to be the fastest way. Create the GPU Particle 2D, call it Boid Particles. Again, create a folder just to stay organized. Save my scene into that. And now we're going to take a look at setting up the shader, just getting set up for this. So we're going to create a new shader material. And so we have that. We'll give that a name. We're going to go out now and get the texture that we're going to be using for this. So this is just a super simple bitmap in the shape of an arrow. I'm going to use to represent the Boids here. So I'm going to add that to my project here, and then add that in as the texture. Now, if you go into our Boid particle scene, you should see that texture representing the Boid right in the center of the screen. Okay, let's build out the particle shader. The first thing we're going to need are the variables for the position and rotation, which is stored in a texture map, and then also the scale that we'll be using in this. Set those both as uniform so we can set them in the GD script. We won't need the start function. In the process, we're going to first pull the position and rotation data, so we'll need the size of that texture map to do this calculation. We get the column by taking the modulus of the index, the size, and then divide the index by the size to get the row. From there, we can pull out from the texture using texel fetch the position and rotation information. The rotation information will go into the transformation matrix in this fashion. Then we'll multiply that by the scale. So now we've got the scale and rotation. And finally, we'll put the position in the last column of the transformation matrix with this code here. Okay, now we're going to connect this to the main function. So we're going to create our texture map that's going to store the position and rotation data. We're going to make that a square texture based on the size of Boids. So we've got 100 Boids. Square root of that is 10. We're going to have a 10 by 10 texture. Create that in the ready function. And we'll create a function called update texture. Okay, now in the update texture function, basically what we're going to do is write the position and rotation of each Boid into this image and then update the texture. That pixel position is reversed. It should be modulus first, then the division to get the proper column and then row for X and Y. I fixed that in the final code that you'll get. Once we have that calculation, we update the Boid texture, and then we will call this function from the process function every frame. Okay, now we need to do two things for these particles. One, we need to set the particle amount to the number of Boids, and then we need to set that texture map that will feed in the data for the position and rotation every frame. We will add our particle scene into the main scene, and then if we run this, we should see our Boids rendered. And there we go, success. All right, so far we've done a lot of plumbing to get to the fun part here, which is writing the Boids simulation. So we're going to need some new variables to control this. We're going to do them all as exports so that we can control all of them from within the user interface here and tweak them to make sure to get them to a point that we like the simulation. Going to create a function that we're going to call every frame that will run this Boids simulation. We're going to do it on the CPU first. It's a lot easier to debug things in GDScript on the CPU than it is in Compute Shader. So I want to get something working here first, and then we'll convert it to a Compute Shader. So we're going to spin through every Boid. This is a real brute force way to do things, just single thread spinning through every Boid. So probably the slowest way you could do this. We've got all these variables we'll use here. We're going to spin through every Boid. Basically, the first thing we're going to do here is check for that friend radius and see who's in our friend radius. Then you see we'll also check who's in that inner avoid radius, count up the number of friends, storing their velocity and midpoint, and we'll add all that data to our existing Boid. So basically what we're doing is calculating this new velocity vector based on the friends, the midpoint of the friends, and the avoids. Then we're going to clamp that velocity to some max velocity we've defined. What you see happening here is we're going to set the position to wrap. So if you get to the edge of the screen, you'll basically reappear on the other screen. I've just found that that's a much more fluid experience. And then finally, we set those final positions. Now we're going to call this function from the process function. Then you'll see we update the data texture. And if we run this, we should see these little Boids flying around and flocking with one another. And there you go. So if this is your first time doing this, congratulations, you just wrote your first Boids simulation. Okay, before we move on, let's do a couple things here. The first thing I want to do is add an FPS so we can see how fast this simulation is running. So just do that with this window title. And then what I'm going to do is go in here and disable VSync. Otherwise, you'd just be locked to 60 frames per second, 30 frames per second for the VSync. So instead, if I disable that, it'll just let it run at the max FPS. Last thing I'm going to do here is make this a floating window so we can run our simulation and then play with these variables and see how they affect the simulation. So you can see on the title, we've got 100 Boids running at 114, 112 frames per second. I can go in here, I can adjust the min and max velocity, see how that affects the Boids. If I turn down the separation factor, they'll all cluster together more tightly because they won't be avoiding one another. I can go in here and I can reduce the friend radius so they won't see as far. That can create nicer little groups. And yeah, you can play around this and experiment and see what kind of behaviors you like the best. But it's just awesome to be able to set those variables right in the Godot engine like that. And this floating window makes it a really nice way to test and play around with prototypes before you get your final design. So anyway, have some fun with this, and then we will look at what we can do with compute shaders to speed this up. Okay, so let's run a little experiment here. If we set the number of Boids to 150 and run this again, we look at the performance. It's dropped from 112 frames per second to 50 frames per second. So if we wanted to take a quick peek and see what might be causing that, we can go into the profiler here, and you can see the frame time, and then you can look and you can plot some of the other things you can see. The process function is taking a long time, particularly to update Boid CPU. So we know we have a bottleneck with that function. That's what we're going to attack with the compute shaders. Okay, just a small housekeeping task here. We've got a debugger warning here complaining about the integer division. We're just going to go in here and cast this to float to clean that up. Again, this is reversed. It should be modulus first, division second for the proper column row. Fix that in the final version. Run this again. See that debugger error goes away. For the compute shader, I'm going to use VS Code. You can't actually edit these, as far as I know, within Godot. I'm going to create a new folder called Compute Shaders, and then I'm going to make a GLSL file. We call that Boids Simulation, and this is where we're going to write our compute shader. What I'm going to do here is basically show side by side of the code that we wrote for GD script and the Boids simulation, so that we can sort of mirror what we did. Now, I'm not going to go into great detail on all these aspects of the compute shader. I learned enough to get this done, so you have to put a header in here, compute version 450. We need to set up our layout here. 1024 is the max X work groups that my GPU can run, so I'm going to use that. Then we need to lay out all the different variables we need. So here you see the position and velocity buffers, so they'll hold all the position and velocity data. This list of parameters should look familiar to you. These are all of the Boids simulation settings, plus some additional things that we'll need, image size, viewport size that we need to pass to the compute shader. And then finally, this Boid data is the image where we will be writing the information that will ultimately go to that texture map that goes into the particle shader. Okay, now within the compute shader, we're going to write the main function. This is basically copying what we did, with the big difference being this will run in parallel for every Boid. So there's no need to loop through all the Boids. This is where you get the huge speed up. It's going to run all these Boids in parallel, doing all these calculations. The syntax will be slightly different. You can compare the files and see, but the code is essentially doing the same thing. You just need to sort of convert the GD script to GLSL code. Let's see, a couple other things that counted here. The rotation, had to use the dot product to calculate the rotation, and it's very important that you check for is not a number. Had some bugs with that drove me crazy with Boids disappearing. Here we are clamping the velocity to keep it within the max velocity. Then for the wrap, we don't have that nice little wrap function to call, but if you just take the modulus of the X and Y size, you can basically create the same behavior. Then we'll write the positions into velocity and position buffers. And finally, we will store the information in the texture map that will go, like I said, back to that data will go to the particle shader to render these. Okay, let's connect our compute shader to GD script. First thing I'm doing here is I'm just going to disable the printing, because I'm hoping we're going to be able to run quite a few Boids here, and I don't want to spew all that to the log. So I'm going to create several variables that are going to be needed for the compute shader. Again, I'm not going to go into details on what all of these things are, but you can see you get your rendering device, your compute shader, pipelines, bindings, and then these buffers are basically the data that we'll be using to shuttle back and forth between the compute shader and the GD script. I'm going to create a function to basically set up the compute shader at the beginning. We get our rendering device from the rendering server, and we'll use that to load that GLSL file that we wrote. You can see right there. And basically from that we can create our compute shader and our pipeline. Next thing we'll do is set up the buffers for the position and the velocity. Okay, I've made a couple helper functions when I was doing this for the repetitive pieces of the code. So one of them is generating these vector buffers and generating uniforms. So here's the generate vector buffer. Basically, create a packed vector to array, and then a data buffer from that we can return. Now the uniforms, you notice that that last number, the binding, it is critical that that matches what you put in the compute shader when we set up our variables there. There's a binding number. So position is bound to 1, velocity, or position is bound to 0, velocity is bound to 1. If you mess that up, you're gonna have some problems. Here's our parameter buffer. This is bound to 2. I made a custom function for this. This is where we're going to basically pass all of that information about the settings for the Boid simulation, the time, the size of the window for wrapping, all of that information that the compute shader will need to perform the same calculations that we did on the CPU with GDScript. So I've got those buffers, those uniforms all set up. The last piece that we need to create here is the texture that we'll be passing in. This will store the position and velocity and rotation. I'm using a 16-bit. I just want to make it no bigger than it needs to be. This gets expensive the more Boids you get. Passing the data is an expensive part of the operation. We set up that texture, create a buffer for that, generate the uniform that's bound to 3, as you can see there. Then we create our bindings array. Again, put those in the right order for the array. And then we want to call this function from the ready function. So one of the things I want to be able to do is switch off between GPU and CPU. So I made this variable like just a Boolean that I can check if we're running on the GPU and set up the compute shader. Okay, now let's write the function to run the compute shader each frame. So I'm going to create a new function. Call it update Boids GPU. I'm going to pass the time into that from the process function. We're going to need to do some housekeeping here. So this parameter buffer that has all these parameters, we're going to free that each frame so we don't have a memory leak, and then regenerate it with the latest data, update the uniform set. Then we will create a compute list. And this is important. This next step, when we create this dispatch list, you can see I set the number of work groups and the X equal to the number of Boids divided by 1024 to ensure we run enough threads to get all of the Boids. And then I have a function already sync that will basically wait for the GPU to finish the calculation. Now we need to set up the function to get the data back from the compute shader and put it into that texture that will be used by the particle shader. So we're going to go up to our update data texture and add a new path for that to happen. So again, if we're simulating GPU, we're going to do it this way. From the rendering device, we're going to call it texture get data. We're going to get that Boid data buffer, and then we're going to use set data to set that on the Boid data image. I'm going to move the old code into the non-GPU path, and then at the bottom there you call Boid data texture, and you'll update it with that Boid data. Okay, we're getting close, I swear. The next thing we need to do is actually call these functions every frame. So within the process function, we're going to set up our calls there. We're actually going to call sync at the beginning of this function because by the parallel nature of the GPU running separately, we want to kick off the simulation, let Godot do everything it needs to do, and then ask for the GPU to finish when we get to the next process function. So that's why I'm calling sync Boids GPU at the beginning of this. And at the end of the function, for simulating GPU, I will call update Boids GPU. Now, in order for that to work, we need to make sure that we make our first update Boids call in the onReady function. Otherwise, the first time you hit this function, it will complain that you haven't called that yet. So we'll add that. And then there's some important housekeeping that you need to do when you exit the tree. Let the GPU finish syncing and then free all of the RIDs that you created along with the rendering device. Okay, so now that we've done all that work, let's give this thing a test. If we run it, you'll see hopefully everything will still look like it's running normally, except if you look at the frames per second, instead of running at 55 frames per second, on my machine I'm running closer to 1,000 frames per second for the same amount of calculation we were doing before. So let's see if we can increase the number of Boids and how the performance behaves. So let's try 1,000 Boids. So here's 1,000 Boids running on the GPU. We can see we're still holding close to 1,000 frames per second. So we have a lot more headroom for our simulation here. So let's really run some experiments and try to ramp it up. Okay, let's try a bigger number with this. How about 20,000? We'll break out the parameters to a floating window. Again, we'll run this simulation. I'm going to make it bigger to give the Boids more room to spread out. And first thing you might notice is this doesn't really look necessarily like 20,000 Boids. And that's because of these settings, they're all sort of stacked on top of each other. So we'll make a couple of adjustments here to the friend radius, Boid radius, speed them up. And the big change that will affect this is by increasing that separation force, they really spread out. And now you can get a sense of the scale of what 20,000 Boids simulated looks like. Still running at 80 frames per second on my machine. But congratulations, now you've gone through the basics of writing a compute shader. You can get some appreciation for the difference between a single threaded operation that needs to spin through all of the Boids sequentially to do this versus parallel processing of a GPU where each Boid can run its calculation independently. Just a huge performance increase. Where do you go from here? Well, if you want to jump from 20,000 Boids to say 100,000 Boids, probably the next big thing we need to implement would be spatial binning. Basically, the idea is you divide the world up into these small bins, and then for each Boid, rather than having to look at every Boid in the world, it will only look at the Boids that are in the grids near it. So I have a little visualization here. You can see, for instance, so this Boid, the gray Boids are the grids that it's looking at, the green Boids are the friends, the red Boids are the voids. And so if there's enough interest, I will implement that in the next tutorial video. Some other fun things that you can do with this, you can color them by the number of friends they have. That'll give you a lot of interesting results. Also, one of the ones that's really fun is coloring them by the direction that they're heading. So you can get some really interesting colors and patterns there. And then I also added this mouse avoidance, and so as you move the mouse around, the Boids will basically fly away from it, so you can get some interesting behavior there as well. So as I said, if there's enough interest, I can keep going with this series and take you further down and show you how to do these things. But you have the basics now to create a compute shader, and thank you so much for watching. I hope you enjoy it. Hey, thanks for taking the time to watch this video. Here's some resources that you could use. I'll put these in the description below as well. Code is free for you to use on your projects. I hope you find it helpful. Please leave comments for ways I can improve this in the future. Thank you so much.